Hi, my name is Kimberly Ames, and this is my presentation, Evolving Robot Paths with Genetic Algorithms. In this demo, I'll show how genetic algorithms can be applied to pathfinding problems in robotics and compare their performance in two different maze environments. What is a genetic algorithm? A genetic algorithm is a type of search and optimization method inspired by natural selection. Instead of solving a problem directly, we evolve a population of candidate solutions. Each candidate is scored with a fitness function, which tells us how good it is. Then, through selection, crossover, and mutation, we generate new candidates. Over many generations, the population evolves toward better and better solutions. For this project, I applied a genetic algorithm to a pathfinding problem. Imagine a robot in a grid world filled with obstacles. The robot starts in the top left corner marked S, and the goal is in the bottom right corner marked G. Each candidate solution is a sequence of moves like up, down, left, or right. The fitness function rewards solutions that end closer to the goal, penalizes collisions, and gives a big bonus for reaching the target. To evolve solutions, I defined a chromosome as a sequence of 60 moves. For selection, I used a tournament method where the best of a small group is chosen to reproduce. For crossover, I spliced together segments of two parents. Mutation randomly changed some moves to introduce variety. Finally, I used elitism, which preserves the top solutions from one generation to the next. I tested the algorithm on a random maze with about 20% obstacles. In this experiment, the genetic algorithm was not able to find a complete path. The fitness plateaued at low levels, and the robot never reached the goal. This demonstrates one of the main limitations of genetic algorithms. In highly complex or noisy environments, they may struggle to find feasible solutions without carefully tuning or hybrid methods. Next, I tested the algorithm on a hand-designed maze with a clear, solvable path. In this case, the algorithm steadily improved across generations and eventually discovered a path to the goal in 51 steps. This highlights the strengths of genetic algorithms with the problem structure and fitness function gives useful feedback. This comparison chart shows the difference clearly. In the random maze shown in red and orange, the fitness stayed low across generations and never reached a solution. In contrast, the handmade maze shown in green and blue had fitness that steadily improved until the robot reached the goal. This comparison highlights both the strengths and weaknesses of genetic algorithms. They are flexible and adaptive, but their performance depends heavily on problem structure and feedback. The main takeaway is that genetic algorithms are powerful optimization tools, but not guaranteed to succeed. They work best when the fitness function is well designed and the search space is structured. Random mazes highlight the limitations while the handmade maze shows their potential. This project illustrates how genetic algorithms can evolve useful robot paths through trial and error. Hey, robots there. In conclusion, This project demonstrated both failure and success cases of genetic algorithm pathfinding. Seeing both slides is valuable because it teaches us that GAs are not magic solutions, but tools that require careful design. They are a good fit for many AI applications, especially when exact solutions are hard to compute. Thank you very much for watching.